Now that we've talked about a couple different gas laws, we want to put them all together. That way it'll be more realistic, more of what actually happens in real life, as we're dealing with multiple variables at the same time. Now the first law we studied Boyle's law. We know that Boyle's law is going to be pressure times volume is equal to pressure times volume. We talked about Charles' law, which talks about volume and temperature. Volume 1 divided by temperature 1 is equal to volume 2 divided by temperature 2. Now, Amundsen's law is pretty similar to Charles' law. What this says is that pressure divided by temperature is equal to pressure divided by temperature. So, similar to Charles' law, as temperature increases, the pressure also increases. As temperature decreases, pressure also decreases. And last but not least, we have Avogadro's law, the guy famous for talking about moles. So what Avogadro's law says is that volume 1 divided by N1 is equal to volume 2 divided by N2. Now N, when we have a lowercase n, that means number of moles. So what this says is that as you increase the number of moles, you increase the volume, which makes sense. If you add more gas, it's going to increase the volume of that gas. So we can put them all together and form our combined gas law, which is going to be P times V divided by N times T is equal to, on the right side, P times V divided by N times T. Now we can see how we got this law together. Both pressure and volume are directly related to temperature and the number of moles. So when we combine all these equations together, we end up with this arrangement of variables. The other thing you need to keep in mind is that temperature must be in Kelvin. Just like using Charles' law, we always need to use our temperature in Kelvin to solve combined gas laws. So let's take a look at an example. We know that we have a volume of 7,500 liters, temperature of 270 Kelvin, and a pressure of 1.2 atm. So we want to use this equation. We already know P1, V1, and T1. We want to say what's going to be the volume of the balloon if pressure drops to 0.90 atmospheres and the temperature decreases to 230 Kelvin. So, for these, we need to know pressure, volume, and temperature. Remember, if the number of moles stays the same, if anything is constant, we don't need to worry about it. We're only looking at the variables that change. So, we've got V1, T1, and P1. And over here we've got P2, our ending pressure, and T2, our ending temperature. Once again, we don't need to worry about number of moles because it's constant, it doesn't change. So we plug in our numbers, 1.2 times 7,500 divided by 270 is equal to 0.90 times volume 2 divided by 230 Kelvin. So what's left is needing to solve for volume 2. And to solve for this, we want to cross multiply, just like in Charles' law. So what we do is we multiply 270 times 0.9 times volume 2. So on one side, we've got all these variables. On the other side, we're going to cross multiply these, and end up with 230 times 1.2 times 7,500. And our next step is to solve for V2. So we're going to multiply 270 times 0.9 and end up with 243 times volume 2 is equal to, multiply all the numbers on this side, is equal to, that is 2,070,000. So last step is to isolate volume 2, get it by itself. We divide both sides by 243 and end up with volume 2 is equal to 8,500 liters. So, in this way, we remember when we want to cross multiply, making sure we're keeping track of our units and solving for volume 2. Now our next problem, we have the volume of a gas at STP is 22.4 liters. STP stands for standard temperature and pressure. But it's not always, volume and temperature and pressure are not always standard. So now we know at 12 degrees Celsius, the volume is going to change to 55.0 liters. And we want to find out what the new pressure is. So to do this, we need to know what STP actually means. When we say standard temperature and pressure, we mean 0 degrees Celsius and 1 atmosphere. So, we know that our starting temperature is going to be 0 degrees Celsius. Our starting pressure is going to be 1 atmosphere. First off, we don't like stuff in Celsius, so we want to convert this to Kelvin. 0 plus 273 gives us 273 Kelvin. So now we know our T1 and our P1. We also, so again, we know our temperature 1 is 273, pressure 1 is 1 atm. Volume 1, our starting volume is 22.4 liters. Now our ending temperature, T2, is going to be 285 Kelvin. We do 12 plus 273, which gives us 285 Kelvin, is going to be T2. And we know that our volume, our ending volume, V2, is going to be 55 liters. So now we want to solve for our ending pressure. We want to solve for P2. We set up our equation. Once again, we don't need to use number of moles. We don't need to use N because that is remaining constant. It's not changing. Plug in the numbers that we have. So we've got 1 atmosphere times 22.4 liters divided by 273 Kelvin. So that's P1 times V1 divided by T1 is equal to pressure 2, what we're solving for, times V2, 55 liters, divided by 285 Kelvin. Next, to solve this, we want to cross multiply. So we have 273 times 55 times pressure 2 on one side is equal to 1 times 22.4 times 285. Now we want to try to get pressure by itself, so our first step is to multiply these numbers together. We know we've got 15,015 times pressure 2 is equal to 6,384. Divide both sides by 15,015, and we end up with pressure 2 is equal to 0.43 atm. Make sure we've got our units backed up to pressure. In this case, we're using atmospheres. So this is how we solve for pressure, and that is how we solve a combined gas problem.